Hello, so this is lecture 3 of Math 5700. And in this installment, we're going to talk about section 2.2 of the text, which is about the axioms of probability. So let me pull up the whiteboard and get started. Okay, so we want to talk about the axioms of probability, section 2.2. And the idea is this: the way we motivate is we think of having an experiment, like flip a coin, toss a die, toss a pair of dice, and then the set of all outcomes, the set of all possible outcomes of the experiment is called the sample space. And it's almost always denoted by S in the book, capital S. Okay, so so let me give you some examples. So if we toss a one-sided die, a six-sided die, tossing a six-sided die, what is the sample space in that case? Well, we can think of that as the set 1, 2, 3, 4, 5, 6, since there are no other outcomes when you toss a die. You wouldn't get 7, for example. Okay. What about if we toss a pair of dice? What are the outcomes when we toss a pair? Say we have a green die and a red die, so we can distinguish between the two. So then we record the green die's value of the toss, that's any number between 1 and 6, and the red die, which is any number between 1 and 6. So you're going to get 1, 1, 1, 2. So the green die has value 1, the red die has value 2 now, 1, 3, 1, 4, 1, 5, 1, 6. Then we have 2, 1, 2, 2, all the way up to 2, 6. We have all the way from 6, 1, 6, 6. So the set of all these possibilities, how many are there? Well, 6 times 6, or 36 outcomes. And these, I've listed all the outcomes. So the sample space in this case is this set here, in that case for tossing a pair of dice. What about the lifetime of an LED light bulb? Well, this is more complicated. So we measure the lifetime as a unit of time, and it's the set of all possible values x. This means such that x is between 0, well, that means it has no life at all. It's a dead bulb, and then maybe it could live for any length of time. Practically speaking, it won't live to be, a billion hours, but we have to allow for that. So it's the set of outcomes is any number between 0 and infinity. So this is a half open interval, 0, infinity. So the set of outcomes can actually be infinite. The sample space can be infinite. Here's another example. So this is actually an interval, right? Another example would be to pick a whole number between 0 and infinity. In this case, the sample space would be 0, 1, 2, 3, 4, 5, etc. It's a set of natural numbers. Usually it's denoted by this, called the natural numbers. Okay. Um, okay, so that's the sample space. Now I want to talk about events. So I'm going to clear the screen. What are events? An event is any subset, let's call it E maybe in this case, of the sample space. So this symbol means subset of. So for example, if S is equal to 1, 2, 3, 4, 5, 6, that's the case of a single die. And I ask, when you flip a die, what happen? We could have the event 1, 3, and 5. These are all the outcomes which are odd numbers. So you toss a die, you could ask whether the outcome is odd or not, and that would be the event of odd outcomes. So I would like to point out here that there are two events that are always available to you in any sample space: the empty event, so the empty set, and there's also the event given by S itself, okay, which is the largest event that you can possibly get. So these always exist in every sample space. Okay. All right. So I want to talk about next operations on events. Maybe I'll number this as 2. Now I'll go to 3. Operations. Well, the operations I'm thinking of are all the operations you can do with sets and subsets. So first of all, there's the operation of union of events. Suppose you're given two events, let's call them E and F, inside the same sample space, S. Then we have union, which is the union of E and F is given by the symbol here, U, E union F. And this is the set of all X in E or in F. In other words, this is the set, I'll do it in set notation, X in S, such that X is in E or X is in F. So that's the union operation. That's a larger event. Then there's the intersection, which computes the overlap between E and F. So you have EF. Sometimes it's called E, they use an upside down symbol, upside down union symbol, but the book writes EF, and this is the set of all X in E and in X in F. So it has to be in both sets. This is an OR, and this is an AND. So this in set theory notation would be the set of all X in S such that X is in E and X is in F. Okay. For example, what about the event you roll a pair of dice? So S is outcomes, the sample space of all outcomes, 1, 1, dot, 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 6, 6. This is the case of rolling a pair of dice. And E will be the event roll 7 or 11 when you toss a pair of dice. And then E would then be given by the following pairs: 1, 1, 6. Well, actually, I'm not saying this right. Let me do it over. E would be 7, roll 7, and let F be roll 11. So that's how I want to say it. So roll 7, and F will be roll 11. So E would be 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and then lastly 6, 1. Those are all the ways the outcome adds up to 7. And then F would be, I guess, 5, 6, and 6, 5. There's no other way to make 11. There are only 2 ways to make 11. So what is E union F? That would be putting both of these together. So it would be 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1, 5, 6, 6, 5. And what does E intersect F? That's empty because you can only, if you make it 11, you're not making a 7 and vice versa. Okay, so that is the example of union and intersection. Let me go up to the upper right-hand part of the board. There's also complementary events. That would be C. So that would be like if you have an event E, an event, then E complement, usually the book denotes it by E with a C as a superscript. That's the set of all X in S, X lies in S, such that X is not an element of E. This means not an element of. So for example, if we go to let S be, let's let S be 1 through 6, let E be 1, 3, or 5, then E complement will be 2, 4, 6, right? Those are the ways an outcome of rolling a single die, you get an even number. Okay. Then lastly, there's one other thing we should mention. There's the inclusion of events. So this means, when I write this, it means that every element of E is an element of F. So X, this means that if X is an E, then X is also an element of F. Okay, F is a larger event. Okay, so now that we have the basic operations, we can talk about the algebra of events. So that's what I'm going to do now, but I'm going to have to erase the screen to do it. Okay, so algebra, event algebra. I'll put that in quotes. So these operations have certain properties. First of all, one has commutativity. E union F is equal to F union E. And also E intersect F is equal to F intersect E. That's pretty clear from the definition. Then we have associativity. That would be E union F union a third event G. Suppose we put the F union G together like this. We first take F union G and then we take the union with E. That's the same thing as E union F taken first and then taking the union with G. And similarly, we have something similar with intersection. E F G is equal to E F intersect F with G. And because it doesn't matter how these parentheses are put, we can now write in both cases E union F union G without parentheses, and in this case E F G, since it doesn't matter where we put the parentheses, how you parenthesize the expression. Okay, so this is associativity. We also have distributivity. Distributivity is the statement that if we take, for example, E union F, and then intersect with G, that's E intersect G union F intersect G. And there's something similar that goes on when you take E intersect F and take the union with G. That's E union G intersect F union G. So what these examples show is that union is somehow like, I'll put in quotes, addition, and intersection is something like multiplication of ordinary numbers. Okay, there are a couple of more interesting identities. For example, if we take E union the empty event, you always get back E. So this is like, the empty set is acting like the additive identity 0. It's like 0. And then we also have ES equals E. E intersect S, the sample space is E, so S is acting like 1 in this case. Okay, and there are a few more identities that are also very useful. If E is contained in F, then, and that's if and only if, F complement is contained in E complement. In other words, if E is smaller than F, I mean, you could sort of draw a blob, E is a subset of F, then anything that's not in F won't be in E, and that's what this is saying. Okay. Now, it's typical to represent these pictures by Venn diagrams, and a Venn diagram is usually you have the box, where S is the sample space called the universe in set theory. Venn diagrams are natural to set theory, a way of depicting sets. So you have the set S, and then you have the event, say, E, and you have the event F, and the overlap is indicating the intersection. So that would be E intersect F that represented there. So for example, if you want a triple intersection, E intersect F intersect G as depicted by EFG, that would EFG would be this thing here. So this is E, this is F, this is G, then the shaded region is EFG. Okay. Likewise, if you have E inside the sample space, then everything outside of E, I'll shade it in some way. This would be E complement. Okay. Very good. Okay, so now I want to talk about another identity, which is quite useful. It's called De Morgan's laws. I'll first state it in the most simple case. So let me clear the screen. Okay, so De Morgan's laws. What do they say? There are two of them. It says that two events E and F in the same sample space, if I take their union and then take the complement, that's the same as E complement intersect F complement. That's one of the results. And the other result is saying that if I take E intersect F complement, then that's the same thing as E complement union F complement. By the way, I should have said on the previous slide that E complement complement gives you back E again, right? Okay, and you can actually recover the first statement from the second statement by applying the complement, taking the complement again to the second expression. So it's enough for me to prove the first law, the first De Morgan law. And the way we'll do it is to show both inclusion this way and inclusion the other way. So we want to show that E union F complement is a subset of E. By the way, I sometimes do subset this way. I also use this symbol. They both mean the same thing. So E union F complement is a subset of E complement F intersect F complement. So that's the first thing we want to show. So let's show that first. So let's see. So that means if X is any element of E union F complement, we must show that it lies in E complement intersect F complement, right? So what does it mean for X to be an element of this complement? It means that X is not an element of E union F. So, but that implies that X is not an element of E and X is not an element of F. Okay, but if X is not an element of E, that means that X is an element of E complement and X is an element of F complement. But and means intersection, so X is then an element of E complement intersect F complement. Now we're going to show the opposite direction. We're going to show that E complement F complement is a subset of E union F complement. How do we do that? Well, we take X to be any element of E complement intersect F complement, and that means that X is an element of E complement and X is an element of F complement. But that means that X is not an element of E and X is not an element of F. So it's in neither set. But if it's in neither set, then an X is not an element of E or an element of F. So that implies X is in E union F complement. And then we've shown that the inclusions go both ways. If one set is included in another and the other set is included in the first set, then they have to be equal. So this means that E union F complement equals E complement intersect F complement. That's what we had to show. So that's De Morgan's laws. And now I want to, without proof, state the generalization of De Morgan's laws. I'll do it on the next slide. This is the most general case. So let me call this generalized De Morgan. It goes like this. You're given a bunch of sets, E1 through En, a bunch of subsets of the sample space, and then we take the union, I goes from 1 to N of E sub I. That's, of course, the same thing as E1 union E2, union E3, etc., all the way up to E sub N. And we complement that. And that's going to give you the intersection, I goes from 1 to N, of EI complement. And a similar thing goes for intersecting, I goes from 1 to N, E sub I complement. That's the union, I goes from 1 to N, of E sub I complement. So these are the two general forms of De Morgan's laws. We recover the previous version when we have two sets, when N is 2. So, so that's it for this lecture. We finish section 2.2 of the text.